failure. Otherwise, you don't know how long something will last. So we'd like to do most of that ourselves before the customer gets the parts, right? That should make sense. Well, so we'll do that by doing the intrinsic characterization. Remember, that's the integrated circuit itself. We're going to try to break it. Give it a little higher voltage than it's supposed to have, a little higher temperature, a little, higher current, higher stresses than it's supposed to have, and hopefully accelerate the failures. We want to find out what's the weakest link. There's another intrinsic type thing, the manufacturing qualification. 400, 500 steps or more in manufacturing in the wafer fab. We qualify that manufacturing line by running test circuits. And then we have to test the reliability to see if everything's behaving like it's supposed to. And we might need to tweak some of the processes. This film thickness has got to be a little higher, this implant's got to be a little bit higher dosage, whatever it may be. So we know a lot about the reliability before we ever designed an integrated circuit, because we tested the individual components and we know how they're going to act. And now we put hundreds, thousands, millions, billions together on one circuit. And then we test it again. And that's the product reliability qualifications in a package and all set to roll. So we test it every possible way and stress it extra so we can try to make it fail. Besides that, we have our own process monitoring and specific process control. We might detect defects in our wafer fab. And so if we do that, of course, we're going to try to fix them. We find out what level they're at, predict what kind of failure they might cause if we left them there. So we can get all of these kinds of information basically from within the wafer fab, things that we can measure right there. Then when wafers are finished, we'll get the electrical test field improvement. If we can get more good circuits, typically that's a good sign for reliability too. And then we'll use other techniques to take advantage of the fact that we're actually testing something about each wafer. So neighborhood analysis, in other words, maybe there's a few bad circuits in one part of the wafer. Why is that? What's going on? It might be indicating that the neighbors, even though they're passing, there's a risk that they might be unreliable if they have just a little bit of the same problem that the others do. And so we might actually throw out some extra ones around that neighborhood to make sure that there couldn't be a reliability problem getting out to the customer. DPAT is dynamic part analysis testing. Average part average, I knew it was wrong. Dynamic part average testing. So again, we look at groups and see if is this group of die behaving the same as the next group of die, and then something different, it gives a warning to us. Statistical bin limiting. We test everything, and let's say one parameter of the threshold voltage of a particular transistor is not looking the same over on this side of the wafer. Statistically looks different than what we should be seeing. So we'll use that test bin. Bin is like, I just came from my boat, you size a potato, you can throw the 3-inch ones over here and the 4-inch ones. Each one goes in a different bin. Each test is in its own bin, so to speak.
Do you still do SHMU plotting?
Yes. So SHMU is accelerating the voltage and frequency and see when things fail. And then, so that's used for integrated circuits. That we would typically use something like that when we detect a problem, not on regular production that's already supposed to be good. We'll use it more for characterizing. Okay, so electrical test gives us a lot of feedback. That's the first really electrical feedback on the circuit that we get. To perform electrical functions, we get to test those. We have to do it by putting probes, or if it's a finished product, we'll put the circuit into a socket So either way, but that's very good information for us, and we try to squeeze out whatever reliability information we can. Then the customer returns. That means we sold the parts and then something went wrong and the customer says, no, we're returning this because it doesn't work right. So that's not so good. Everybody hates that. And it actually is very expensive for both the customer and us because we've got to respond quickly. We have to try to analyze, okay, what's wrong with our circuit? And what's the cause? And how did that happen? And did that same thing happen on other circuits that we might have shipped already? Or what can we do about it? All these things. It's very stressful, but it's the best data that we get because it's real customer data. We can never generate data for the customer. So we love to have customer data. We just don't like the fact that it failed before the warranty period because that doesn't make us look good. Makes the customer angry, etc. Okay, and then sometimes, once in a while, we get customer feedback that's other than returns. It says, hey, that's the best circuit we ever got. I want another one. You know, it's not quite like that. They want lower price. But sometimes we get feedback about how the customer is using our circuit that we didn't know. We don't know what mission profile, what we call it. We don't know that. We don't know what they're going to do with it. So sometimes we find out things from the customer, hey, it worked in this application, but not in this one. And then that helps us figure out maybe where the weakness is or how we can make our next circuit more robust.
How about like upgrading? You know, where the commercial avionics folks will take the commercial parts and upgrade them to meet certain.
So we just had a discussion about something like that today, actually, just before I came. We have arguments with the military folks. We sell some military circuits, so we have to jump through a lot of hoops to qualify these for the military, and then they don't want very many. So it costs a lot for us to do some. At the same time, the military will buy off-the-shelf parts. And we have lots in the catalog. We have thousands of different parts. And so they'll buy just off the shelf and put them in the same system with the expensive one they bought from us. But then they'll complain that the off-the-shelf part isn't behaving as reliably as the custom part that they ordered from. And we have to say, well, wait, it meets the specifications we said. You're trying to use it for an upgraded application that we didn't know anything about. If you want one of those, we can make one. Anyway, it's an interesting game. I'll continue here. In different colors, this is trying to sort of summarize some of the things that I've gone through. We start out with the quality of design rules. If those are good, that's going to ensure reliability for those designs because the design rules were properly done. Then there's the design of the part, following the rules and not just the rules, but some experience people have. Don't put these two things next to each other because it's going to cause extra heat and air. There's a lot of flat art that's involved. But those are sort of things related to the design. Now we have the materials we're going to use. So crystal, silicon material, and the copper metallization, and lots of different chemicals that we use in different materials. So how did we specify? We have to specify, like if sulfuric acid that we use, we used to call it electronic grade way back when. Especially pure acid that we buy. It has less impurities than the normal stuff because it's electronic grade. Then it became semiconductor grade. That's like double, triple better. It's just really, really clean and costs a lot more, but it's a semiconductor grade materials. Well, we do it because the quality of the materials that we're using is very, very important because we can have latent defects resulting that we can't see, we can't even detect this. They may be so
You're using
rare.
these acids for your etching process?
Etching, cleaning, lots of different processes in the wafer fab use different acids, other chemicals. So we have to specify what we really need. If it can't have chlorine in it, we've got to say 0 chlorine, and then we've got to go find somebody who can create that for us and deliver it routinely. And years ago, that was very difficult. These days, you just pay for it. Lots of people can do it, but it's costly. But it's worth it to us because this is how we build the reliability in. That's why I have this. Okay, now there's the manufacturing process. When I say the design of the manufacturing process, we want the manufacturing process to be so good that every transistor that gets created all the way through all these steps is going to work right without any question. And that way we can make tens of billions of transistors on one circuit, and we'll make 100 of those on one wafer. And we really do it. It's amazing that we can make billions of something and tens and hundreds of billions of interconnects that hook them all up. I mean, there's no other kind of thing that does a process with such good result, except building of integrated circuits. So we take advantage of that, and we have the process control. That's how we build in the reliability. It has to have superior process control besides the superior materials. Okay, then there's the use conditions. We have to say what voltage, what environment is allowable to operate our circuit. If we do all those things right, we'll have a reliable integrated circuit product. And underline here, we ship to the customer. The customer has got to enforce the limits that we set. They can't go above the absolute maximum rating in voltage or put it in seawater when they weren't supposed to, or whatever, right? So we're depending on the customer to preserve the reliability once we ship it. And here's something that we're always up against. This is true for everybody, not just semiconductor industry. Deming quality triangle. So W. Edwards Deming is a famous statistician. And this triangle is cost, schedule, and quality. And there's some other ways you might see this. Under quality, I'm thinking reliability. Quality don't have anybody do that. So any project you're doing, you pick 2 of these, 3, and the other one's defined for you. You cannot make a choice on all 3 of them. You pick 2, and it defines what the 3rd one's going to be. So if I say, okay, I've got a budget. I don't see here. So, okay, I have a budget I have to stay within. I have a schedule I have to stay within. I've defined it. I no longer have a choice about what the quality is going to be, because that's defined. Did I build in quality and reliability testing, et cetera, into the cost? If I did, yeah, good. What happens when the schedule starts slipping and they say, okay, ship, you're done? What happens? It's the quality that suffers. That's what we're all used to. So what we have to say from a reliability standpoint is, you set the reliability first. If it's that important, you set this one first, and things like cost and schedule come after. You figure out what it's going to take to make it reliable, and now our budget and our schedule is made to fit that. And you put a reliability engineer on your design team. Easy to say. Doesn't happen. In reality, it doesn't happen much. I just want to mention failure mode and effects analysis, MEAs. Those came about, I think, starting in the space program, the military back in the 1960s. Started thinking of, you want to predict what might go wrong before it happens. and then figure out how likely is it. And the ones that are serious problems and likely to happen, you better address those before you even do your design. So it's a great concept. What we find is that we're doing FMEAs typically to catch up because it's time for an audit. And so we have, in some of the departments where I work, we have a ways to go. We need to have reliability engineering involved earlier to think about what might go wrong. And then we can address some of those issues ahead so they never happen for the customer. So that's the ideal way.
It's also a way to do your risk assessment.
Yes.
Design weaknesses that you say, well, I'm not going to fix this, but I'm going to monitor it. And then you can assess the risk to it.
Yeah. So the FMEA by itself, it doesn't happen all by itself. There's typically all kinds of different teams thinking about potential causes, potential failures, what are the root causes and the failure mechanisms that can happen. Anyway, there's a lot of information that comes together so that you can create a good FMEA. And so you'll know the risks and you'll know a lot of other information if you go through the process. The idea is to do it early. If we want to design for reliability, we'll do this ahead. Think carefully about what could happen, what could go wrong, what kind of failures might happen.
Yeah, you can also do other kinds of analysis that are very similar to it, like a fishbone, cause and effect, Ishikawa.
We do them all.
Oh, you do them all?
They're all
all
rolled into this.
encompassing in this.
Yeah. There are some industry standards. I showed you one of the JEDEC. I showed you a piece of this JSC 47. There's the Automotive Electronics Council and the mill standard specs, which are so old, everybody hates them. Because they're just too out of date and they never get updated. But we have these standards available to us, and so we make use of them, and we participate on the committees that help generate these. And so eventually, especially the JEDEC ones will be getting updated for things that I need. Meanwhile, the Auto Executive Council is going to keep updating to make the specs tighter and tighter.
How about 38510 or 38535? You still use those?
I don't personally.
Because 883 is just the test methods. But the way to
those
qualify, right, the qualification process, like you talked about, your design qualification, your lot by lot variability, your lot acceptance testing.
Yeah.
That's all from the higher level standards, like the 535.
So I
510.
personally end up dealing more with the JEDEC and the APCs.
Okay. So more of industry as opposed to mill.
Yeah, because we have a military rail engineer that deals specifically with
Okay,
military.
so you're more on the commercial.
I'm more commercial, yeah. So I'm sorry, I don't deal with those. So I listed the ones that I see the most often. But the idea is that it helps customers to have standards, because then when we say we've done 1,000 hours H2O tests, they know what it is. Because there's actually a method described. Everybody does it the same way. It helps the customers and it helps us, because we can buy equipment that's made to do that test, because they built it for against the standard, basically. And so other people at other companies can get the same type of equipment that does the same method. So it's beneficial to everybody to have the standards. And again, most people don't realize, but I participate on some of the committees, and so do our other rail engineers. So that it's a very slow process. We just had a new revision of one of the specs I worked on. It took 3 years to get it through the system, and it was finally approved yesterday. I mean, it was like, yes! After 3 years, right? Okay, but it's just a little thing. There's lots of other specs that are still, or documents that are out of date still, and we need to update them. But anyway, the companies need to help participate so that we can improve our standards.
Since you mentioned physics of failure, do you get involved in any of the VETA standards? Like the VETA 51?
I haven't.
Just curious.
Again, JEDEC and ADC are the ones I see. Yeah. Industry standards. So, okay, we're approaching the last few slides here. The climate for reliability is changing in my business. I already mentioned a little bit about automotive industry, which is our company's biggest customer base. So the automotive industry is driving us to try to get even lower parts per million. That means we ship 1 million parts, and we ship 50 billion parts a year. There's plenty out there. If we have failures, we get some back. So anyway, the automotive industry is driving us to go lower and lower. They don't want any car to have a defective part, period. And we make parts, and other companies, of course, there's so many electronic parts, but in your brake system, your airbag controller, in your dashboard, and a whole bunch of different, your sound system, everything. Some of these things are more critical than others. The stabilization, engine controllers, exhaust monitoring, the cameras everywhere. We make camera chips, infrared camera chips for night visions. Okay, so we make all these different kinds of circuits. They all have to work. Of course, you all want them reliable. And so you purchase your very expensive car, you don't care which, if something fails, you don't care which of the systems is just bad.
Depends on who you are, right? If you're a reliability guy, you care about what your car is doing.
If you're a reliability, you'll buy a different kind of car. Yeah. So anyway, it's this idea that the consumers don't want to have a failure happen on their car. And it's mostly electronics. And so, okay, that means every part has got to be working right. So I read an article, I can't remember the whole details, but it was something like if we shipped our product to 3.4 part per million, like the Six Sigma standard, that a car would be on the road about 5 minutes before a failure. Completely unacceptable. The operating at that kind of level is just nowhere near good enough because there are so many circuits. The chances of having one that's bad is getting higher and higher and higher. And so as a supplier, we have to drive our defect level down.
As far as sensing, so I was talking to some guys from Intel, and they were telling me that they're looking at putting more and more prognostic sensing, kind of tying in our discussion.
Yes, absolutely.
Yeah.
So,
Yeah. Oh,
are
well,
you guys looking at doing that? Putting like pressure
Well-
transducers on your sensor, on your circuits?
whatever the customers want.
Temperature sensors. Well, I mean, just part of your standard offering, right? It's just not an option, but a standard. Because like Intel's saying, you can't run this at a certain temperature, so you have to have
Right.
these huge heat sinks, and you have to have these fans blowing on. I mean, not one fan anymore. It's gonna be like 3 fans inside of your desktop, right, or in your server. So what if the fan fails, right? So how do you protect yourself as a supplier, saying, I know that this part had exceeded its stress limits, right? So they have sensors, right? So the sensor could be just a simple 1 or 0. It tripped a certain threshold, and now it's saying you went over the temperature rating, or you went over the G levels for vibration or shock.
Yep. So we have the technology to incorporate sensors all over the place. It's a question of whether you want the sensors in with your integrated circuit that makes it more expensive.
Yeah, put it on the monolithic.
It takes more room. So a big microprocessor, you can do that. Somebody's paying hundreds of dollars for the one circuit.
But how about like a high power MOSFET? One that if it fails, it can cause huge electrical overstress and potential catastrophic effects.
Yep. But if you're only paying 50 cents for it, we're not gonna put a
Well, how
sensor
much
on.
could it cost? You know, it's tenths of a penny probably, to drop a little sensor on there
All depends.
and add a pin, right, that looks for a 1 or a 0.
Sounds easy, can be done.
That's where we're going with autonomic systems and
Right,
AI.
so as a supplier, we're gonna
Self-driving
design,
cars, the
Yep.
car is gonna need to know, right? It's no longer a person listening for a, rough condition. It's the system detecting, I have a problem.
Yep.
Right?
So-
I don't feel good. Something, I'm not dead yet.
that's
I
right.
don't wanna know when you're dead. I wanna know when you're not feeling right, so you go to the doctor, right? So when the car says, hey, I'm not feeling right, I need to take it into my maintainer, my mechanic, and get something fixed.
So what a company like mine will do is find out from the car manufacturers what they need. And we'll design whatever it is they want, and we'll tell them how much it costs, and then they decide if they want to pay for it. If the technology exists, they can get it. We can build it, right? I mean, it can be done.
Yeah.
But there has to be a demand, because we can't just
I would
spend
think
millions of dollars
there's a
developing something
supplier-
and not have a.
there's gotta be a cost benefit from a supplier point of view. If you look at how much money you spend on doing root cause analysis on your returns, and a lot of times you spend a
And we
lot of
do.
time and money to find to find those results, and you can't even make that determination. As opposed to having a device now that you can read it and there's your truth. There's your trusted device that tells you, I know this bit was flipped, and the only way that's gonna happen is if this thing was shocked, like say 100 G.
Oh, right,
Right, or it was put in water, right? The cell phones, you can tell when they're put in water.
right.
They don't
Apple-
ask the customer anymore, they know.
Right, Apple has the sensor built in, so it can tell
Right,
if
so
it's in the
there's a
water.
humidity sensor. Now those new MEMS sensors have the temperature, the humidity, vibration, and pressure. So all four.
Yep.
Little, tiny MEMS devices can tell you all four of those things.
Yep. So the suppliers can build whatever there's a demand for.
Yeah.
We're not as likely to go out on a limb
And
and
invent-
design something that we think somebody might want. It's just too expensive. It's many millions of dollars to develop a product and millions of dollars to go through reliability testing. So we can't do it unless there's a for sure customer. So
How about
Always
change
a trade-off.
subjects? How about counterfeit parts? Do you deal with that a lot?
So we haven't detected counterfeit parts, to my knowledge.
Nobody
Here's the
returned
part
something
I
to
deal
you and you opened it up and looked at the marking
Right,
and said,
no,
this
we-
isn't our part.
We read about it, yes. We read about them in China, taking apart all the boards and posing them off and then reselling them.
Right.
But no.
I was at an IEEE meeting at the Boston chapter. I used to live in the Boston area. And we had the VP of Analog Devices Quality talk to us. And he said the thing that I spend the majority of my time on is counterfeit parts.
So I don't know from on if we have that problem. Okay. I deal with a lot of the customer returns. But we've never had one that gets blamed on being, not ours kind of thing. So